Welcome to today's lecture. आज के lecture में we are going to start the new topic of DC machines. Let me open the book for you. Okay, you will find this topic relatively easier than the AC machines because in the AC machines you have all the stuff about the complex algebra, so you are going to skip all of that. The algebra for this is simple, and most of the concepts are uh, what you have already studied before. This page. Page. Right, I'm going to be sharing the book with you. Here is the book. Okay, so this topic is DC machinery fundamentals and starts from page number 404 in your book. And we are going to do this example today. And the result that we are going to drive is what we already know from our previous knowledge of this course, as well as the AC machines discussion. So we are going to first take a simple example of a very simple DC machine in which the armature, uh, in which the rotor, rather, the rotor is just composed of a single, the rotor is composed of a single loop of wire, and we are going to see how this single loop of wire experiences a force if the machine is being utilized as a motor, or how it induces voltage if the machine is uh, used as a generator. Okay, so this is a very simple model of the machine, and one difference from this machine is that in the AC machines we have seen that if we provide, normally the main field is on the rotor. If we consider the synchronous machines, the main field is on the rotor, and uh, sometimes we supply AC voltage to the stator, as in the case of synchronous motor, and sometimes we extract AC voltage out of the stator, as in the case of a synchronous generator. In both of these synchronous machines, the main field is considered to be on the rotor, and the armature is considered to be on the stator. And in the case of an induction motor, we provide the three-phase AC supply to the stator, and that produces a rotating magnetic field. So the main field is on the stator in that case, and we do not give anything to the rotor. The rotor is basically uh, it induces the voltage. So in the case of induction motor, the armature is on the rotor, and due to the inductive effect, the rotor starts to rotate in the same direction as the rotating magnetic field produced by the stator. In the DC machine, we are going to consider this simple example. There's only one rotating loop on the rotor, and there's some diagram here that I want you to see first. Basically, the diagram shows, okay, the diagram shows that we have a permanent magnets being used on the stator, which is stationary. And the key thing to note about the permanent magnet being used as the main field in this case. So the main field in this case is on the stator, and there's a single loop of wire uh, which is attached to some axle, so that that single loop of wire could rotate. If it is a generator, we are going to give it mechanical energy to make it rotate. If it is the case of motor, we are going to give it some current, and it will produce some torque, causing it to produce mechanical output from an electrical input. Okay, so I want you to look carefully at this diagram number A, which is being flashed. Let me, okay, so this is the permanent pole magnetic field being created by permanent pole. So the main field is on the stator. when you consider this loop of wire, so these are the two ends of the loop of wire. It is being uh, converted into a rectangular loop. So just follow my pen. So the loop goes like this. It turns right like this. Then it goes through inside of these poles like this, rotates like this, comes back, goes here. Okay, so this is one loop of wire, single loop of wire, which is being uh, constructed in the form of a rectangular loop. Okay, and there the two ends of the wire are over here. In the first case, we are going to use it as a generator, I guess. Yes, we are going to use it as a generator. So this simple example is being used to demonstrate the effect of a generator. And to be precise, since we are doing DC machine, so this is a DC generator. And what happens in a DC generator, we give it some mechanical motion. So we are giving it the mechanical motion and we are causing this loop of wire to rotate in a counterclockwise direction. So this omega m is basically in a counterclockwise direction or opposite to the direction of a regular clock that we have. And the loop of wire is calibrated. This loop of wire, which is inside this magnetic poles, it's calibrated as having four sides. First side is AB, second side is BC, third side is CD, and the fourth side is DA. Okay, so we are going to consider what is the impact of the motion of this single loop of wire when it rotates in an anti-clockwise direction inside these magnetic poles. And one key thing to notice that the poles are having curved surfaces, okay, or rather circular surfaces. So one semicircle is formed by the North Pole and another semicircle is formed by the South Pole. When the pole pieces are curved, it has a very natural effect, and the natural effect is that no matter what is the position of the coil, in whatever angle it is, the uh, the magnetic field will always be perpendicular uh, to the sides of the wire A, B, and CD. Okay, so in whichever direction it has rotated. For example, if you look at the end view of this diagram, this is the end view of this diagram. So in whatever direction, for example, the coil has rotated through, you can see that the field will always be the perpendicular to two sides of the coil, which is this side and this side, and the field will always be parallel to the other two sides. Okay, so the field will always be perpendicular to sides AB and CD. Okay, B will always be perpendicular to sides AB and CD, and B will always be parallel to sides uh, DA and BC. Okay, so in whatever angle it has rotated, due to the fact that the pole sides are curved, so it will always be, the field will always be directed radially, and when the field is directed radially, so it will always be perpendicular. So like over here, the fields is directed radially, the field lines are going like this. So whatever the direction of the coil, these two sides will always have the magnetic field perpendicular to them, and the other two sides will always have the field parallel to it. So what is the consequence of this? So now this is the top end view of the same coil. So these two sides are always perpendicular to the field, and these two sides are always parallel to the field. So when we are going to rotate it, we want to see the effect of some induced EMF. And what will be the induced EMF if the coil is rotated clockwise, as shown in this diagram number 7.1D in the front view. So for the induced EMF, okay, we always use which rule? We always use the right hand rule, Fleming's right hand rule. Okay, this is the generator. So we always use the right hand rule. So we take our, for example, if you want to look at this side, and we are giving it motion and we want to find the direction of current. So you take out your right hand, and second finger is the direction of current. First finger is the thumb is the direction of motion, and first finger is the direction of the field. So if you align the thumb in this direction of the velocity VAB and you assign the first finger B in the direction of the B, I'm talking about this part of the diagram, this part of the diagram. So you can see that the second finger will be pointing into the page. Okay. So this is what we get here, that the current is going inside, the induced current is going inside, and we apply the same right hand rule over here, then the induced current is coming to be out of the page. Okay. So for the two sides A, B, okay, for the sides A, B, the current is going into the plane of the page like this. And for the side CD, the current is coming out of the plane of the page as shown over here. And we get this using the Fleming's right hand rule. And when we look at the other two sides, this sides BC and DA in a moment, before that, there is also two arrows mentioned here which are showing the direction of the force. So it is a generator, the primary effect is the induction of voltage, but you also have a secondary effect which is the direction of the force. And this direction of the force will be a secondary effect as a consequence of this. So you can get this direction of the force using the uh, left hand rule. So now again you take your second finger, point it in the direction into the page. I'm talking about this part of the diagram. First finger in the direction of the field, so the thumb is going to point downwards in this direction. So this is a secondary effect because primarily you are running this machine as a motor, but you also know that there are sometimes secondary effects in a machine, that whenever a current is induced and that current is inside a magnetic field, then it experiences a force. Okay, so you have the secondary effect. So we have already seen that using the right hand rule, we can predict the direction of the current in these two sides of the coil. What about the remaining two? In the remaining two sides, you can see that the direction of the current, if the current is going like this, obviously, then in this part of the coil, the current direction would be this. And in this part of the coil, the current direction would be like this. So now what happens is, for the sides BC and the sides DA, the direction of the current becomes parallel to the field. And when the direction of the current becomes parallel to the field, so we know the formula for induced EMF. The formula for induced EMF is V cross B dot L. Okay. And whatever the direction for V cross B and the magnitude, we dig to a dot product of this with L, where L is the direction taken to be same as the current in the wire. Okay. So now what happens is, again, we look at the first side AB before we do all of the sides in turn one by one. So let's look at the first side AB, segment AB. There it is here. Okay, in the segment AB, we know the formula is this V cross B. Now what happens in segment AB is we want to find the direction of V cross B. Okay, we already know that there will be some induced EMF because all of these vectors are mutually perpendicular. We have applied our right hand rule and we saw that V is mutually perpendicular to B because V is at a tangent to the circle, B is coming radially towards that circle, and L is the direction of the current. This length vector L is taken as the same, and which is also mutually perpendicular to both V and B. So what is the direction of V cross B? So if we look again at this figure, sorry, it's downwards. So if we look at this front end view, okay, and V cross B direction, we want to find the direction of V cross B for segment AB. What is the direction of V cross B? So we again take the right hand tool, first finger in the direction of the velocity, second finger in the direction of the uh, field, and thumb is pointing inwards. Okay, so the resultant of V cross B is inwards. Okay, and the direction of L is also taken as the direction of the current, which is also inverse. So we know that it is V cross B sine 90, okay, multiplied by the length of the wire L, okay. And now we know that this vector and this vector both are in the same direction. So this is cos of 0, and I know cos of 0 is 1, and I also know sine of 90 is 1. So this magnitude is simply equal to V into B into L. Okay, so the magnitude of induced EMF in segment AB is simply V into B into L. Okay. Now look at the next segment. In the next segment, we look at the BC segment. This is the segment number BC. And in the segment BC, I know that, look at the front end view. Okay, in the segment BC, or look at the top end view, the current is going in the direction from B to C. So it is the far end of this coil. And in the direction of BC, we can see that BC is also directed in a radial direction, and B is also directed in a radial direction. So, and obviously V is tangential to that circle. So when we look at this same logic for the segment BC, the induced EMF comes out to be zero, because when we look at the quantity V cross B, it is either into the page or out of the page. How it is either into or out? So if we look at the segment BC in this particular half, okay, so now you know that in this particular half, uh, you want to find the direction of V cross B. So you know that V is directed tangentially upwards. Okay, V is directed tangentially upwards. So first finger in the direction of V. Okay, second finger in the direction of B. Sorry, first finger in the uh, V. We want to find the direction of V cross B. Okay, so first finger in the direction of V, second finger in the direction of B. So the thumb is going to point into the inward direction. So that is what it is saying. And when you do for the other end, the other half of segment BC, thumb will be pointing out of the page. So that is what exactly it is saying, that either the vector V cross B is into the page or it is out of the page, while L is perpendicular to the plane of the page. So L is like this, and either V cross B is into the page or V cross B is out of the page, and the direction of L is always taken as the direction of the current. So L will always be perpendicular to this. So when you apply your relationship V cross B dot L, so the when you are calculating the cos of the angle, this will be equal to V magnitude of B to sine of the angle between the two. The angle between V and B is obviously 90, no problem there. When you are doing this L into cos, then you again get cos 90, and cos 90 is equal to 0. So it will pull the whole EMF down to 0. So we have done two sides of the coil. The remaining two sides of the coil are the same. When you look at the side C uh, DC, it will again be equal to VBL, just like the segment AB. And when you look at the other last segment DA, it will also have an induced voltage 0, just like before. So when you look at the total EMF, you sum the EMFs across the two sides, four sides of the coil, and you know this side and this side were 0, and these two sides were equal to VBL. So the net voltage will be 2 VBL. So this is the induced voltage which will be generated over one single loop of wire when it is being rotated through the curved pole pieces. Now the problem is when you take this induced EMF and you try to map it on a graph, so you see that for every half cycle it will change its direction. Okay, so the magnitude is 2 VBL, but for half cycle it is positive 2 VBL. For the negative half cycle it is equal to minus 2 VBL. Now why this direction changes is, the direction changes because when this side this side, this is the side AB of the coil, and when it starts from here, it is under the south pole of the magnetic field. It is still under the south pole, south pole, south pole, south pole. And as soon as it switches from the south pole to the north pole, the direction of the current in this side will be reversed. First, it was going inwards, and then it will start to come outwards. And similarly for the this side, which the direction was outwards, as soon as it crosses the north pole into the south pole, the direction would become inwards. And this reason is that the direction of motion becomes reverse. So when you look at the perspective of this side, the velocity vector is upwards. But as soon as it crosses the south pole into the north pole, the velocity vector becomes tangentially downwards. So this the reversal of the velocity vector actually causes it to also reverse the direction of the induced current. So these two sides are only producing the currents. The other two sides are just they have induced EMF. The other two sides are just supporting this current because the loop is connected in series, but they have no induced EMF of their own. So the induced EMF is only on this side AB and on the side CB. Okay, but the other two sides are indeed carrying the current, the same amount of current, because the loop is connected all in series for the four sides of the coil. So total EMF is this, but it will be pulsating. Okay, and why this value stays constant? It is not like a sine wave. Okay, because it is not like a sine wave, it is constant because the fact that the magnetic field is always perpendicular to the wire, the two sides of the wire which are producing EMF, sides AB and the sides CD, they both are always perpendicular to the direction of the field, and the velocity is also constant. So there is nothing which is to suggest that it will have some uh, non-constant behavior, because V is constant, B is constant, and the length of the wire is constant. So it is not going to behave like a sinusoidal wave. It is going to behave like a constant DC voltage, only which it changes direction after every half cycle. Why it goes to zero instantaneously? The reason it goes to zero instantaneously before going in the reverse direction is when the plane of the coil is like this and your curved pole pieces are like this. Okay, so as you know, the field is directed radially for this case. Field is always radially, and when this side of the coil is just moving in this direction and this side of the coil is just moving in this direction, so uh, for suddenly for just one moment, uh, uh, the B field, the B field, as it goes in the air gap, suddenly for one moment, uh, the B field goes to zero, and that is why, because of the air gap, there is no B field over here, and all the B directions are going radially. So for just this moment, when it doesn't find the field, the induced EMF goes to zero. Okay, just momentarily, when the plane of the coil is perpendicular, doesn't find the B field, it goes to zero, and just immediately after that, again, it receives a perpendicular B field. So just in the air gap, okay, so it says that under the pole faces, its magnitude of EMF is this, and just when it passes through the air gap, the B field suddenly goes to zero, so there's no induced EMF. Again, the B field returns, but the direction of velocity changes, so the direction of the EMF also. Okay, now we can also drive some more generic expression. The same expression VBL to VBL can be derived into more specific uh, representation according to the construction of the machine. And that construction is, we can consider the pole surface area. So we have two poles in the machine. One is the north pole, one is the south pole. So we want to consider this area and this area, okay, which is the area of the pole. And the area of the pole, this, if you can see this, this is a surface area of a half a cylinder. Okay, and what is this surface area of a cylinder? The surface area of a cylinder is 2 pi r. If you have a circle like this, cylinder like this, and you want to find the surface area, which is the area of the curved surface. So if you just cut through a scissor through it and you stretch it, that curved surface area just make like a rectangle, and the circular part here is just the circumference of the circle, and this part is just the length of the coil. So this is the length of the sides AB or sides CD, and this 2 pi r is the circumference of the cylinder, and one pole area will be equal to half of this, so it will be equal to pi into r times into L. So one surface area is this, another surface area, the surface area of south pole is pi rl, surface area of the north pole is pi rl. So if we substitute this expression over here, and we substitute the fact that V is equal to omega r. Yasser, please switch off your video, please. Okay, so you know that for circular dynamics, the tangential velocity is equal to radius multiplied by the angular velocity omega, which is of the the rectangular loop rotating in the magnetic poles. So if you substitute that in place of V, so in place of 2 VBL, in place of V, you are substituting R omega M. So it is when the rectangle is under the pole faces, it is equal to 2 VBL. When it is beyond the pole faces in the edge air gap, it goes to 0. So you substitute V as R omega M over here. And you also know that you can substitute this, that the pole area is equal to pi RL. Okay. So now you are substituting that RL with this gadget. So RL is equal to AP over pi. Okay. So RL is equal to AP over pi, meaning gadgets being the same. So the induced EMF is equal to 2 over pi pole area, a single pole area multiplied by the magnetic flux B, magnetic field density B times omega. Okay. And you also know that the flux is equal to the magnetic field density times the pole area, B into AP, which is the pole area. So you can substitute this with the gadget phi. So this is a very simple result driven in a very simple way, but it gives you an idea that induced EMF is equal to, it is a function of some constant. Okay, so you can say this is some constant times the flux of the machine times the rotating speed of the machine, because you know that induced EMF is equal to minus rate of change of flux. So the rate at which the flux will change will be depending on the angular speed of the rotor of this machine, because that will govern the way in which the flux is changing inside the loop. Okay. So this is something which is a previously known result, and now we have just given it some specific shape for the DC machines. So induced EMF in terms of the more generic things are equal to flux equal to the rotating speed times some constant K. Okay. So this constant K will vary depending on the structure of the machine. And flux and omega M are just generic quantities. They are not dependent on the construction of the machine. Okay. So if you were taking AP and you were taking L and other stuff, so that becomes specific to the construction of the machine. But over here, these quantities become generic. Okay. So how we can get a DC voltage? We were getting a pulsating DC and alternating DC voltage, rather we should say, because the DC was also switching its direction. So you cannot exactly call it DC. It was fluctuating AC you were getting out of it. Okay. So how you can get the pure DC which doesn't change its direction? For that, what you will have to do is you have to attach some device which is known as a commutator. Commutator are two copper rings, semicircular copper rings. You attach one copper ring to one side of the coil and the other one to the other side of the coil, and every half cycle when the direction of the EMF is going to be reversed, so the side of that coil is also switching to a different. For example, this side of the coil and its direction of induced current was this, And when it so the direction of the EMF will also be correspondingly proportion to this. But when it goes and switches from one pole phase to the other, the direction of the current and hence the induced EMF also changes. So what happens is, just when it is going to swing in its direction, the other side will come and take its place. Okay, because this side is going to swing its direction, so this side will now be attached to this side, and this side will come and it will continue to resume in the same direction. Okay, so you must have already studied this in physics also in your previous years. So instead of the AC voltage, you are going to get a, DC voltage, but it will still be a pulsating DC voltage, because few times when the plane of the coil is in the air gap, it goes to zero, because there is no presence of the B field in that air gap. Okay, but it is for a very minor amount of time. Just like the case of a generator, we could also run this single loop of wire like a motor. And in the motor, again, we use a commutator, but we give it a supply. Why we give it a commutator here in the case of a DC motor is, we want to reverse the direction of the current after every half cycle. Okay, so in order to have a unidirectional torque. Okay, so for example, your machine was in some particular configuration like this, and the direction of the current was outwards here and inwards here. So the direction of the field can be given by the Fleming's left hand rule. So if you take your left hand and you take the first finger in the direction of the B field here, I'm talking about this part of the diagram, and you take your second finger current and make the second finger come out of the page like this, your thumb will be pointing in this direction. Similarly, for this side, your thumb will be pointing in this direction. So it will be having a counterclockwise torque. So the machine will also begin to move counterclockwise. Okay, so now you can easily see here that the direction of the current has to be reversed once the coil passes this vertical position in order to get a unidirectional torque. Okay, so you have to use this commutator that that allows this side of the coil and this side of the coil to reverse their polarity once after every half cycle, so it keeps on getting a unidirectional torque. So for example, this side needs to have a current reversal, so when it will switch on this side, it will get a current reversal and the torque will be unidirectional. If you hadn't done so, the machine would become just oscillating, because it would not be getting a unidirectional torque. After every half cycle, the direction of the torque would not be reversed, or rather, the direction of the force would not be reversed to get a unidirectional torque. So you have to switch the direction of the current after every half cycle, and you do this again with the help of a commutator. Okay, so now we want to analyze the torque of this rotating loop. So the formula of the torque is well known, you know this, I into L cross B, in which I is just multiplying like a scalar to this. So you just need to consider the cross product of L cross B, and L is the length of the wire, and the direction of L is always taken as the current, okay, as the direction of the current. So the torque on the segment will be equal to R into F into sine theta, because you know that the torque is taken with the perpendicular distance with the axle. Okay, so uh, this is the generic formula. Okay, and why we take this component is because we need to take the force and the perpendicular distance. Okay, and we always know that the angle between R and F is always the angle between RF and the R and F is always tangential to the circle. R is always acting perpendicular to this. Always this angle will be 90 degrees for curved pole faces. Okay, so whenever we have curved pole faces, this theta will always be 90. But if you have straight pole faces, then you have to take this component. Because in the special case of curved pole faces, B is always acting radially, and the velocity or the force is acting tangentially, and always the angle between R and F will be equal to sine 90 degrees. Okay, so when we look at the segment AB, the direction of F is this, B is this, and the current is coming out of the page. So what we need to do, we need to calculate L cross B. So the direction of L cross B, L is taken as the direction of the current. So again, in order to find the resultant of L cross B, you can take your first finger in the direction of current, second finger in the direction of the field, and the L cross B is the same direction as this F. Okay, so L cross B is in the same direction as this F, same direction as of the F, and the angle between here I've already told you is always 90 degrees L cross B angle. So you just simply get this IL, and the direction is tangential to the direction of the motion. So this is the force on the side AB, and torque is you have to just multiply it by R. And the angle I've already told you is always 90 degree for curved pole faces. So it will become RILB. Okay. Similar will be the case of the opposite segment CD. But when we look at the segment BC, it will have no force. Why segment BC will have no force? So let's look at the diagram. Segment BC is the far end of this coil. And in that far end of the coil, you can see that whatever the current direction, the current will always be parallel to the B field. Okay, because the far end, the current direction is also radial and the B field is also radial. So whenever you are going to be calculating this property, L cross B, L cross B will always be zero because the two quantities are parallel to each other. Okay, that is what exactly it is saying. So similarly to segment BC, segment CD torque will also be zero, and segment CD torque will be equal to segment AB torque. Two sides will experience a torque, two sides experience no torque. So you enter sides of the two sides torque and it will be equal to 2RIL times B. We can again apply the same logic that one pole face area is equal to the half of the surface area of a cylinder, which is equal to pi RL, and flux is equal to that pole area times B. So when I substitute these gadgets here, the torque induced expression neatly summarizes into a constant K times the flux times the I. And this makes sense because torque is basically just a function of the force, and the force is just a function of the B field and the current in the B field. Okay, so the B field or the flux is here, and the I in the rotor part is here. So the torque induced is simply equal to expression K times phi times I. Okay, so these are just the two simple derivations that I needed to do. Now we are going to go and start the topic of DC machines, which is much simpler than the discussion we had on the AC machines. So this was just some fundamental knowledge that you needed to have, that what is the purpose of a commutator that you use in a DC machines, in the DC generator as well as the DC motor. So we can now skip and go to the actual topic of the DC machines. You will find it is much more simpler than the AC machines because you don't have to worry about the algebra of the complex phasors and stuff. Okay, so we are going to look at the DC machines. You can see these machines in your toys. All of the toys of little children, they have small DC motors in them. Sometimes most of them are permanent pole DC motors. Okay, and in the larger DC motors, you may have to use electromagnets to have the B field. Okay, so there are 3 or 4 types of DC machines, and we are going to do in turn. And first, we are going to do DC motors, and the DC generators are just the opposite of the DC motors, so we are not going to spend much time. These are the main types. We are going to do separately excited DC motor. We are going to do shunt DC motor. We are going to do series DC motor. The permanent magnet DC motor is just what we did right now. And then there is a compounded DC motor. We will see if we have enough time, then we are going to do this in detail. Otherwise, I'm just going to tell you the difference of this compounded DC motor with the others. Okay, so our primary objective is to cover and complete these topics: separately excited DC motor, shunt DC motor, and the series DC motor. Okay, and all of these have their different merits and demerits. For example, the series DC motor, it has a high starting torque. Okay, and this shunt and DC motor, it has some property that it has constant, almost constant